All right, let's start off with, I'm sure, the $64,000 question. Have you finished grading the exams? No. Um, Not only are there about 60 people in here, but like an idiot, I thought it was a good idea to do an exam in another one of my classes today. So this weekend I've got about 90 exams to grade, so yeah. My goal is to get it done on Monday. I want to say a couple things about the exam and how I'll do this. So given that we have like 60 people in here, the whole point of doing it via Blackboard was so that I could download the results in one big old spreadsheet. And what I did during our virtual operation last year is I have a big old report template generator, and what it does is I'll grade each of the questions, and it'll generate a custom PDF report for every student in the class so that you'll know how you did on each problem and what the deductions were and why. And I'll send that to everybody in here as an email. So each of you will get an email that'll say something like Engineering 213 grade report, see attached. So everybody will have their own individual grade assessment. I'll also, what I'll do is that'll be your grade. That'll be how you get your feedback on the exam. If anybody wants their scratch calculations, I'll put them outside my office or something. I'll let you all grab those to your heart's content. But I'll wait until I'm finished grading. I have already gotten a couple of questions on the like of, how much is the exam worth, because I was worried I didn't do well. Look, let me say a couple things about that. Each exam in here is only worth 15% of the grade. So I do that for a reason. I could do a midterm and a final, but I don't do that. It means more work for me, but I don't want any one exam to make or break your grade. So, don't worry about that. And I'll tell you another thing is that whenever I developed my teaching philosophy, what I did is I stacked up all the stuff that used to bug the heck out of me when I was a student that professors would do, and I said, I'm not going to do that, okay? So one of the things that I do is I never grade each student's exam. Like I don't grade your exam and then your exam and then your exam and then your exam. I don't do that. I grade problem 1 for everybody, and then problem 2 for everybody. And I do that so that I'm ensuring I'm not taking different amounts from each student, because that used to annoy me. When a friend of mine and I would take the exam, and we'd get the same deduction, or we do the same thing, make the same error, and I'd get more points taken off than they were. I was like, no, we're not doing that. Yeah, so I'm not going to do that to you. And I do really try and pride myself on being fair. We did have a couple technical hiccups, so we had some calculator hiccups and whatnot. I'm going to do my absolute best to not hold that against anybody in here. I really want to try and be fair, and I will do that. I've been a professor for years. I've never really had anybody complain about me being an unfair grader or anything, but I guess my overall point is I bet that you probably did better than you think you did, and it will be okay. Trust me. I gave when I did this exam last year, and it was a completely virtual course. I'll go ahead and say it. I think the exam I did last year was harder, and the averages in the class came out much better than the students expected. I think the average was in either the high 70s or the low 80s on the exam. So you're probably better off than you think. Okay, let's talk about moving forward. So there's an old saying about this course is that statics is really only about 2 things, and that's forces and moments. And so we've spent the past few weeks talking about forces. It's time to start talking about moments. And the formal definition of a moment is going to be utilizing a cross product. And so hopefully you watched that lecture that I pre-recorded that talked about the cross product, and you did homework 3.1, which was due today. Now, I'll go ahead and tell you 3.1 is incredibly short, and given that I know it's been a while since that's assigned, if you didn't get a chance to do that or you forgot, I'll probably accept that till, I don't know, maybe 5 p.m. today, and I won't count any late points on that, just to be nice on that, because I know it was a while since I assigned it. But it's a worthy assignment to do, because the whole point of homework 3.1 is to just talk about cross products. And we're going to be doing quite a few of them, and we're going to start doing those today. So Fortunately, your calculators can do it, and there's a couple of methods that you can utilize to do a cross product. Speaking of, let's talk a little bit about that. Let's recall what was covered in that video. So if I could give a mathematical spirit to what we've been talking about for the past few weeks, test 1, exam 1, was all about adding vectors, right? Vector A plus vector B. And whether we were doing static equilibrium or what have you, that's kind of what we were focused on. Whereas now we're going to be talking about multiplying vectors, okay? And there are 2 ways to do vector multiplication. And so the first method that I showed you was the harder method, which is the cross product, because we're going to be using it today, okay? So mathematically, the cross product, so remember there are 2 ways to multiply vectors. One yields a scalar answer. So vector A times vector B gives you 6, right? We call that the dot product because of the notation that we use. And when you have vector A times vector B that gives you another vector, a vector product, we call that a cross product because we do A cross B. That's the notation that we use. As for how we define the cross product, what we have is we have vector A and vector B, these 2 random vectors. And the idea is that in order to define the cross product, we say, what do we want the goals to be? So we want the vector to point normal to the plane that's formed by A and B. So A and B are 2 vectors in space. They form a plane. Vector A cross B is normal to that plane. It's a way of defining that direction that is consistent for any vector. So remember, a vector has a magnitude and a direction. I remember that problem being on the exam. Exam 1. So the direction of A cross B is normal to the plane that's formed by A and B. And as for the magnitude is the area of this parallelogram. And so the pre-recorded lecture that I did, we were talking about all the algebra and alphabet soup that gets to this. This is how we perform the cross product. And there are 2 ways of doing it. So we basically, when we do all the math, we find that the cross product can be idealized as this determinant. And as for doing a 3x3 determinant, there are 2 ways of doing it. We can use the rule of Serres, which is basically we take these 2 columns, stick them over here. We do all the products this way minus all the products that way. That's one way of doing it. And another way is to do cofactor expansion. So what we do is we say, okay, this term times this determinant. We strike out the row and column and we say it's this determinant. Then we have this term and we strike out the row and column and we say it's that determinant. And then this term, strike out the row and column and we say it's the remaining determinant. We expand along a given row. And then we alternate our signs, so plus, minus, plus. I actually kind of like doing it this way because I think that in the end, it's easier to track your signs. And as for these 2x2 determinants, it's just this times this minus that times that. So we'll probably use that today. Now, where in the heck does that matter in terms of what we're talking about in this class? So we're now going to introduce our second major topic in the course, which is looking at rigid bodies. And if particles were concurrent force systems, in other words, everything we were doing on exam 1 was talking about all of the forces all meeting at a common point. Now they're not going to meet at a common point. So now we're going to be dealing with non-concurrent force systems. That's what I mean when I say a rigid body. In order to introduce the concept of rigid bodies and to explain what the deal is with this concept called a moment, I have a couple of examples here that I kind of want to explain what's going on. So let's look at this example here on the left. How many of you have ever played Jenga? Okay, all right, or at least at a minimum you know what it is. Okay, so let's say I've got a table right here, and I have a Jenga tower right here, and it's in a fairly precarious position. You know, there's some blocks that's been moved around, and it's kind of wobbly, kind of unstable. And let's say I address a challenge to you. I say, okay, I want you to take this Jenga table, and I want you to move it from here to here. But I only want you to use one hand, okay? What would be the easiest way to do that, okay? So I'll give you 2 options. All right, option 1, here's the Jenga tower. I grab it at the top and I push it. Option 2, I grab it at the bottom and push it. Which is the easier way to do it, option 1 or option 2? 2, right? Now, let's talk about why that is, okay? This is going to be probably a little noisy, my apologies. But here's a table. If I want to drag this table across the floor, I don't just, hit it with my pinky. I actually have to pull a little bit because the table is resisting in the opposite direction. What's resisting? Like, why am I having to pull? There's friction between the floor and the table, right? I'm having to overcome that friction. It's the same thing that happens when you try and move a refrigerator across the floor, some furniture across the floor. You're pushing in one direction, and the contact between the object and the floor is pushing in the other direction. With me so far? Okay. And so if I tie this to this Jenga exercise, the reason that I don't push the Jenga tower on top, the reason why I push it on the bottom is because if I want to slide that Jenga tower, right, the contact between the Jenga tower and the table is pushing in the opposite direction. Now, your common sense is saying that if you want to slide that table across that table, you need to move your hand on the bottom, right? Now, the reason why is because you're pushing this way, okay? The table, the friction between the Jenga tower and the table is pushing this way, and so your common sense says keep those forces as close together as possible, right? Because what you want to do to the table, or what you want to do to the Jenga tower, is you want to translate that Jenga tower, but you don't want to rotate that Jenga tower. Okay, so there's a little bit of a difference between translation and rotation. That goes into this example. So here's a mechanic, and this mechanic is trying to apply a torque to this connection on this front end loader, it looks like. And we look at the way that the mechanic is gripping the wrench, and we notice that the mechanic is gripping the wrench at the very, very end. My question is why? Why doesn't the mechanic grip right here? Why at the end? More leverage, right? In fact, the longer this wrench is, assuming the wrench doesn't bend or whatnot, the longer this wrench is, the more torque or the more oomph the mechanic can apply to the connection, right? I mean, if you've ever changed a tire, I'm sure there's a few people in here that have done this. If you've ever had to change a tire and you've got a lug nut that's being a little stubborn, right? You take your tire iron and get a big old pipe and attach it to the tire iron so that you increase that lever, right? Makes it easier to turn, right? So there's something to be said about rotation and how far apart forces are from one another. And this concept of a moment arm is going to come up here in a bit. So the common theme dealing with these two scenarios is that we're dealing with scenarios where forces don't meet at a common point. Now let's get a little bit mathy. Let's talk about statics. Let's take a look at this scenario here on the top right. I got a rigid body, and I got 20 pounds down and 20 pounds up. Well, now hold on. Sum of forces in the x direction. Is that 0? Yeah, there's nothing going to the left and right. What about sum of forces in the y direction? I got 20 down and I got 20 up. So far, according to the principles of static equilibrium, both sum of forces in the x direction and the y direction are satisfied. But is that system in equilibrium? Of course not, right? Because this system wants to rotate, right? If you're driving your car and you want to turn the wheel left, you take your left hand, pull it down, your right hand, pull it up, right? Okay? Just because you might be applying forces in equal and opposite direction does not mean the system is in equilibrium. To this end, we're now going to introduce some new definitions, and I'm going to sort of look at it this way. I'm going to give you a new definition for a force, and that way I'm going to lead into a definition of a moment. So I'm going to now redefine a force as an action on a body that increases its tendency to translate. Okay? If I apply a force, it wants to take that object and move it from one point to another. Translation. And likewise, I'm going to define a new action on a body that increases a body's tendency to rotate, and I'm going to call that a moment. Because what I'm talking about when it comes to static equilibrium is I want to ensure now that bodies don't just resist translation, but rotation as well. Okay? So the formal definition of a moment is going to be defined as follows. And I know there's a lot going on here in this slide, but I'll sort of explain it visually because I think it's a lot easier. Okay? So let's say I have a point of interest. Let's call this little piece of chalk here, that's the point of interest. So we'll call this point O. Okay? And I have a force out in space let's say this little laser pointer here is my force, okay? And I have a point here and a force going like that. Doesn't matter where the force is, don't matter which way the force is pointing for the purpose of the definition, just that the line of action doesn't go through the point, that it's going in a different direction, okay? I propose that the definition of the moment that this force generates about this point is defined as the cross product of R cross F. F being the force vector in question, and R being what's called a position vector. And the position vector is basically any vector that goes from this point to any point on this line of action. So see this laser pointer shooting all the way over here. R could go from here to here, here to here, here to here, here to here, anywhere from that point to that line of action. And I propose to you that if R is defined from the point in question to the line of action of that force, you will get the same computation for moment regardless of what R is. And if you don't believe me, we're going to have an example today that verifies that. The reason why, and we're going to see this here in a bit, because what we're really interested in when we determine magnitudes of moments, so going back to that example of the mechanic applying the torque to that connection, the magnitude of a moment, what we're really interested in is the magnitude of the force times this term d, and I'm calling d the moment arm. And if you look here in this image is kind of explaining it a little better. So here's this force F, okay? And notice how R is going from the point in question to the line of action. And so what I was getting at earlier is that R could go like this, it could go like this, like this, like this. It could go anywhere from the origin to that line of action, and you will get the same answer for the moment, okay? Because what we're really interested in, what we're really interested in is this distance d, and this distance d is the shortest distance from the point to the line of action. So it's sort of this perpendicular distance from this line to this point, okay? And regardless of what position vector you use, you will get the same magnitude. Okay, I think the easiest way to go into this is to do some examples. But one of the reasons I want to show you why the R doesn't matter, like it could point to any point along that line of action, the first thing I want to do is I want to introduce a principle in statics called the principle of transmissibility, okay? What the principle of transmissibility states is that two forces that have equal magnitude and direction are equivalent provided that they fall along the same line of action. And that's a mouthful, I know. So the simplest example I can think to explain what I'm talking about is the tug of war, okay? Now let's idealize the tug of war for the sake of the discussion. Let's say that the rope has no sag in it, that it's perfectly straight, and I got, 6 or 7 folks in blue yanking this way and 6 or 7 folks in purple yanking the other way. How far apart do you think these folks are, these two teams are? 20 feet? Assuming no sag in the rope, would it matter if they were 40 feet away? Or 80 feet? Or 200 feet? Or 3 feet? It doesn't really matter, right? The forces are equal magnitude, the same direction. The idea of the principle of transmissibility is that from a moment perspective, this force and this force are equivalent. Same magnitude, same direction. I can sort of slide that vector along that line of action. See, what we're getting at is this, okay? Oh, my little animation works, yay. Okay, so if you remember the cross product is defined such that the magnitude is equal to the magnitude of this parallelogram, right? So what we've got here is this parallelogram, and notice how what's happening is the base is remaining fixed, okay? So the magnitude and direction of the base is remaining fixed, but what's going on with the top is it's sort of undergoing this weird transformation. So think of the top and what's going on here are different R vectors, different position vectors. So I have let's pay attention to point A. I have a vector going from here to here, 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 etc., right? Different R vectors. one of the nifty things about geometry is that as this parallelogram is going through these weird shifts, one thing that isn't changing is the area, okay? The area of that parallelogram is the same throughout the entirety of this animation because the area of the parallelogram is defined as the base times this term height, because the height is what really matters. So think of the height as the moment arm. So this is why it doesn't really matter what your position vector is as long as it starts at the point about which moments are taken, because we define moments as about a given point, and it ends at any point along the line of action of F. So think of this dotted line as the line of action of the force in question. R can point anywhere. And so this is the reason why moments are defined as R cross F and not the other way around. Does that idea kind of make sense? Let me prove it to you with an example. So here we have a plate, and this plate is supported by some brackets here and these cables here. Doesn't really matter what's going on with the bracket and the cables. What matters is this, okay? So at point C, there is a cable that is supporting this, about fell over there. A cable that is supporting this, rectangular plate. I propose that the tension in this cable is 200 newtons, right? So if I look at point C, there's a 200 Newton force yanking on this plate at point C. And I think that kind of makes sense from a physics perspective, right? If I have this plate, it's going to want to fall down. So the cable's got to hold it back up. Make sense? Right? So what I want to know is how much moment this force generates about a point in question. And particularly, I'm going to look at point A. Okay? Now, in order to do this, what I'm going to do is I'm going to need a definition of this force vector, F, right? And then I'm going to need a position vector. And the position vector has to start at A, and it has to go anywhere to this line of action. So I'm actually going to do two position vectors. I'm going to go from A to C, and then I'm going to do another one from A to D, because both of these point to this line of action. We're going to get the same answer for the moment at the end of the day. Okay? Does this make sense? All right. Let me pull up my notebook here, and let's do some calcs. Oh. And by the way, I tried to make these images a little bigger. Let me do this. Let's do this. This one can be a little small. Let's make this one a little bigger because that's got the dimensions that we want. Because we're going to do our vector in millimeters. Okay. I'll give everybody a sec. Is everybody good? Oh, okay. Good. All right. So what I'm going to do here to keep this straightforward, because I sort of snuck in a little bit of notation and I didn't quite explain it because we're going to go through that in this example, is I'm going to start off with just some point coordinates. And we're going to do these point coordinates in millimeters, okay? So I see 4 points on here, A, B, C, D. Let's do all of them. So let's do the coordinates for A, B, C, D. And to be clear, this is our origin. And I think I kind of cut it off here on the on this bigger image. So this is the z-axis, this is the y-axis, and this is the x-axis. So let me draw those in. Yeah, I think I cut that off when I did that. My apologies. So that's our origin. And so x-axis, y-axis, z-axis. Okay? Let me start off with A. I'll do A. So I propose that the coordinates of A are 0, 0, 240. Okay? Or sorry, no, 0, 0, 320. Sorry. I forgot that and that. So, whoops. All right. So that's point A. Can somebody give me the coordinates of point B? 0, 0, 80. That's exactly right. All right. What about C? Somebody else. Here's point C right here, by the way. It's that one right there. It's the corner of the plate.
300, 0,
300, 0, 400, and somebody else for the last one. Somebody else. Don't be shy. Somebody over here.
0, 240, 80.
There you go. Exactly right. Okay. All right. Everybody okay with that? Everybody good with that? Okay. All right. Now, the definition of a moment is R cross F. So we're going to start off with R vectors. Okay? So we call those position vectors. So position vectors. Okay. Now, for this problem, I'm going to define two position vectors. Okay? I'm going to define this one right here, and I'm going to define this one. Okay? And I'm going to do two separate position vectors because I want to convince you that it doesn't matter what position vector you utilize as long as it originates from the point in question and it ends at the, along the line of action of the force that you're looking at. So the line of action of the force is this line CD. So we're going from A to C and from A to D. We'll get the same answer at the end. Now, so what we basically need is a vector from A to C, okay, for our first one. So we would call that AC, all right? Now, you should know how to do distance vectors at this point, right? Because we've done distance vectors already. We've done them in 3D. I'm going to introduce a new notation that you're going to see in your textbook, and there is a reason why the notation looks like this. We call it a position vector from C, or to C, to C from A. So we call it RC/A. And the reason that we set it up like this is that if you want to find that position vector, all you have to do is take the coordinates of point C and subtract them as follows. So C minus A. And if you do that, that will give you the vector from A to C. If you don't believe me, let's check this out. So what do we get? We get 300, 0, 80. Is that right? So I propose that RCA is 300I plus 0J plus 80K. And one thing I want to be clear about is that this is in millimeters, okay, because I'm sort of skipping that. And let's just see what happens. How do you get from A to C? Along the x-axis, you go 300, no change in the y, go 80 in the z-axis. So that's a way of doing it, and that's the reason why the notation is like this. I'm really sort of utilizing this notation because I want to be consistent with what your textbook is doing, okay? I would honestly be fine if you just said I need AC and just wrote it down, but I just want to be consistent. All right? With me so far? Okay, if you're okay with that, let's go ahead and do the next one. So again, I'm doing two, not because I need it for the problem, but because I want to convince you that it doesn't matter which way you do this. So we need vector AD. And so the way that we write that in position vector notation is a vector pointing to D from point A. And so we take the coordinates of point D, which are 0, 240, 80, minus A. And so we get 0, 240, and then what is that, negative 240? And so R dA is that. And again, in millimeters. I'll give you a sec to catch up on that. But did I go too fast, or is that okay? All right, I got a lot of highlighters here. I'm going to delete those. That's going to bug me. One of the things I will probably start doing now that we have some experience with vectors is I'm probably going to kind of do it like this, where instead of filling in each of these terms like 0 millimeters, 240 millimeters, negative 240 millimeters, is I'll just write the vector and then at the end say it's in millimeters, because we're going to be writing a lot of vectors here soon, and I want to make it efficient. So far, so good? Okay, now, in order to compute a moment, we need position vectors, but we also need a force vector. Now, first off, let me just ask, does anybody remember what the magnitude of this vector is going to be? Based on what it said at the beginning of the problem? 200 newtons. Okay. Now, let me scroll up a little bit. Let's make sure everybody's paying attention. Okay. Has everybody got this? Okay. Let's pay attention to the problem a little bit. Okay. Let's look right here. Okay. First off, this is a 3D problem. Does anybody remember how we define force vectors in 3D? We take the magnitude of the force vector and what do we multiply it by? Remember that vector lambda, the unit vector that we define in 3D, right? So what we're going to need is we're going to need a vector that defines how that force is pointing. Then we're going to have to turn it into a lambda, a unit vector. And then we multiply it by 200. So what we need is a vector pointing this way, right? From C to D. Does that make sense? Because that's the way the force is pointing. The force is going that way, right? It's going like this. So we need a vector from C to D. We need vector CD. So what's an easy way of doing vector CD? Based on what we've been doing for the past couple minutes. Take the coordinates of point D minus the coordinates of point C, right? So the coordinates of point D are 0, 240, and 80. And then point C are 300, 0, 400. So this is negative 300, 240, negative 320. Right? So CD is negative 300I plus 240J minus 320K. Am I going too fast, or is this making sense? Right? And so this is, again, in millimeters. But the reason that I define this force, or this distance vector, is because the distance vector will tell me the direction. And I get the direction by taking CD divided by its own magnitude. So somebody help me out here off to the side. How do we determine the magnitude of CD? You should know how to do that now. Pythagorean theorem. So help me out. I don't think we need to belabor that. Somebody tell me, what is the magnitude of CD? If you want to be quick in your calculators, do you really need to worry about the positives and negatives? No, because you're going to square them and then take the square root. So somebody tell me. I want to make sure y'all are awake this Friday afternoon. What is the magnitude of CD? 500. Do I have a second on that? All right. 500 millimeters. That is correct. So this is going to be so our lambda vector is going to be, what is this, negative 300 over 500? I think I can do that one in my head. That's negative 0.6 plus 240 over 500. What's that, 0.48? And then plus negative 320 over 500. I think that's negative 0.64. Oh, I forgot my IJK. Now, if this is in millimeters, what's this in? Nothing, right? It's unitless, right? This is a unit vector. We took this vector and divided it by 500 millimeters. So what's millimeters over millimeters? Nothing. So this is unitless. Okay? Let me divide these sections up a little bit so it's a little easier to see when you review it later. Sorry, hold on. Yeah, that's fine. So now that we've got our unit vector, what we can do is take this unit vector, multiply it by what to get the force vector? 200, right? There you go. So all right, let me scroll down a little bit. So my force vector is now, so 200 times negative 0.6, I think that's 120 or negative 120, plus 0.48 times 200, that's 96. Plus, and then that's going to be, what is that? There you go. Make sure everybody's paying attention. And so that we're also paying attention, what are the units for this vector? Newtons. All right. So let me stop for a sec and see if this is making sense so far. This should be sort of, so far, I don't think anything we've done right now is hyper new stuff. This is really just a big old review of stuff we've already done, right? We're just doing position vectors and force vectors. Okay? So far, so good? So let's summarize what we've done so far. Let's just make sure that that makes sense. Okay? So I'm going to put right here, I'm going to say moment computations. And so I don't have to scroll like crazy. So we have R, our first R vector, plus 0a, or plus 0j, plus 80k, and then R 0 plus 240j minus 240k. And then our force vector, and this is negative 120i plus 96j minus 128k. Okay, and just again to be clear, this is millimeters, millimeters, and this is newtons. Okay, so what is the definition? Remind me, what is the definition of a moment? Remember, a moment is a vector, and it is r cross f. Okay, so here's the new stuff. Okay, now I propose if you do r cross f for either the first vector or the second vector, you are going to get the same answer. Let's check that out. So r ca cross f. So how do we do a cross product? Okay, so this will test your whether or not you watched that pre-recorded lecture. We set up a 3x3 determinant. We put ijk in the first row. In the second row, we put the coefficients of our first vector, so 300, 0, 80. And then in the second row, we put minus 120, 96, minus 128. Okay? Now, I don't care which way that you do it. You can do rule of Saris, you can do cofactor expansion, you can plug it into your Casio FX115 ES pluses or equivalent scientific calculators. It does not matter. I'm going to do cofactor. So, the way that this works for cofactor expansion is we start with the I term, cross out the row and column, and we're left with this little block down here, 0, 96, 80, minus 128. Then we do the J, cross out the row and column associated with J and write what's left over. And then do the K vector, cross out the row and column, and then in terms of our signs, we alternate, plus, minus, plus, so minus, plus. And that's our cross product. And in order to determine these smaller ones, we just do that minus that. Remember, the determinant of a 2x2, bless you, is AD minus BC. So, for this I vector, what do we've got? We've got 0 minus 80 times 96. So it's going to be a big number. What is that? Minus 7680. Do I have a second on that? Okay. What about J? What's going on here? So this times this minus this times this. What do we get inside this determinant? You got to pay attention to your signs here. Just keep this in mind. We'll worry about this later. What do you get? This times this minus that times that. Anybody? Negative 28,800. So I will have to call him back. I'm getting a call on my office line. So this times this minus this times this is negative 28,800, but because I got a negative out here, we'll say plus 28,800 J. And then what about K? K, we get 300 times 96 minus 0. So 300 times 96, that's also 28,880, isn't it? So 28,880. And that's your cross product, okay? Now, what I think is kind of crazy is what happens if we do the second vector cross F. Remember, we've got two vectors here to do a cross product of. We've got the first vector times f. What about the second vector times f? Let's do that. And I'll walk you through that one. So R dA cross f, again, I, J, 800. Thank you. That would have mattered here in a bit. Thank you. So we do IJK. We do the same force vector on this last row, but the middle row is now our new vector 0, 240, negative 240. Okay? So I'm going to walk you through this one real quick. So what do? We cross out the term associated with, or the rows and columns associated with I, so 240, negative 240, 96, 128. The terms associated with J, 0, minus 120, negative 240, negative 128. And then the K terms, cross out the row and column associated with K, 0, 20, 240, 96. And then minus, plus. So let's see what we get. What about I? What do we do when we get this times this minus this times this? Wait, did I get my signs wrong? Yep, I forgot a negative. Yeah, I forgot a negative here. So this times this minus this times this, what do we get?
Negative 7,680.
Negative 7680, huh? Is that what we got before? Negative 7680? 7680. Huh. What about the next one?
28,800.
And what do you think we're going to get on this last one? I bet 7. Now hold on, we're not quite done. I want to just make sure I'm clear. But do you see how you're going to get the same answer? It doesn't matter as long as the vector goes from A to the line of action of F. It's good. Did you have a question? Oh, okay. Let me just end on one very minor note, and we're going to call it. So I propose then that the moment about point A is a vector, and it is negative, so I'm getting ahead of myself, negative 7680 I plus 28800 J plus 28800 K. All right? Now, in terms of units, we're doing forces times distance. I'm sure some of you in physics would love to start breaking out joules and whatnot, but we tend to not use joules because we like to separate our definition of energy from moments. So we literally would just say that this is expressed in newtons times millimeters. That's how we express moments. We just say force times distance. And we very rarely would express it in like joules or anything. So like in US units, we'll say foot pounds or foot kips or something like that. And that's our answer. Okay? That's it. Now, I think it's kind of cool that you can do two different cross products and get the same answer. But my microphone's kind of expensive, so I'm going to do a mic case drop. So I know, I'm a dork. You know, it's okay. Ask my wife. She'll tell you all about it. All right. You're going to have a homework on this due Monday. And then what we're going to do on Monday is we're going to take this 3D stuff and let's go back to 2D. We're going to talk about moments in 2 dimensions, and it gets a little easier. It's also a little easier to see how there's different ways of doing it, and you get the same answer. That's all I got. Y'all have a great weekend. I hope to have your exams graded by Monday.